Thank you.
All right, it's time to start. So welcome back to the second talk on the series of Rado lectures. It's my pleasure to welcome back Dr. Wang. I just wanted to announce that she has received the 2026 AWM Doctoral Research Prize. I'm going to read a little bit of the biography there. Yet at an early career stage, the quality and quantity of Wang's publications in top journals, including the Annals of Mathematics, Invenciones, GAFA, Duke, GEMS, and ADM, as well as her work in progress, are quite impressive. Her work places her among the top leaders in some of the most influential areas of Fourier analysis and geometric methods. So please, welcome back to the course.
Thank you very much for the introduction, and thank you for surviving the first talk, and thanks for coming back. Yeah, I just put the exercises here for fun. I'm not asking you to do the exercises. So last time we talked about how to use just Cauchy-Schwarz to prove the two-dimensional Kakeya-type conjecture, this Cordoba's argument. And today let's talk about dimension 3. So another exercise is try to think about what goes wrong in dimension 3 in the Cauchy-Schwarz argument. In that argument, if you just use the same argument, but in dimension 3, you will show that any Kakeya set in dimension 3 has Hausdorff dimension 2, at least 2. So in other words, using the Cauchy-Schwarz bond, you would get the union of tubes in R3 is greater than delta. In 1995, Tom Wolfe showed that if a set of tubes satisfies the Kastel assumption and the Kastel-Wolfe axiom and the Brossman-Wolfe axiom, then the union of tubes has a volume greater than delta to the 1/2. This means that any Kakeya set in R3 has Hausdorff dimension greater or equal than 5/2. Here is and as you might remember on the history, people have been stuck at this Wolf's estimate for a long time. With a lot of effort, people only managed to improve epsilon, where epsilon is like 10 to the minus 10 on the dimension. So there is a reason behind it, and it's a deep reason given by the Heisenberg group in C3 that is discovered by Katz, Laba, and Tao in their influential work in the year 2000. So what is this Heisenberg group? H is defined as Z1, Z2, Z3 are complex numbers, and then the Heisenberg group H is Z1 take norm square plus Z2 square minus Z3 square equals to 1. So, and this Heisenberg group example looks very much like the Kakeya set in R3, as with so one feature is that the Heisenberg group contains a lot of complex lines. So to calculate this example, through the point P equals to 1, 0, 0, means Z1 equals to 1, Z2 equals 0, and Z3 equals 0, then there is a cone that is Z2 square minus Z3 norm square equals to 0. And on this cone, we have we have a one real dimensional family of complex lines. How to see that is we can just take, for instance, let's say theta in C, and then theta has and theta has norm equals to 1, and then the complex line will be theta z and z. This is a complex line, and that's one of those lines. And as we know that there is one real dimensional family of theta in complex numbers with norm 1. So through this point in the Heisenberg group, it contains a one real dimensional set of complex lines. And then we can do double counting and show that the Heisenberg group contains a four real dimensional set of complex lines. Because this is so if we identify C3 with R6, then this is a hypersurface in R6. So the Heisenberg group has real dimension 5. And then if we do double counting, 5 plus 1 minus 2, because a complex line contains two real dimensional set of points. So we get four real dimensional set of complex lines. And then if we also know that this the complex lines in the Heisenberg group are not concentrated in any convex set. So if we have an analog of the Kastel-Wolff axiom and Frossman-Wolff axiom in C3, the Heisenberg group also satisfies an analog of the Kastel-Wolff axiom and Frossman-Wolff axiom. And we have just said that the Heisenberg group has real dimension 5, so it equals to 5 halves times the dimension of complex numbers. So this example is a sharp example for Wolff's argument, in the sense that it satisfies the Kastel-Wolff axiom and Frossman-Wolff axiom, and it has dimension 5 halves. Which means that in order to improve Wolff's bound, so remember this 1995 bound has been a very difficult bound to improve. So in order to, the reason is precisely because the Heisenberg group, in order to improve this bound, we need to distinguish the Heisenberg group example in C3 and the Kakeya set in R3. So for a long time, people think, okay, the Heisenberg group example contains some parallel lines, and the definition for Kakeya set is that we have one line in every delta separated direction. We have one line in every direction. So maybe one should think about, one should use the property that a Kakeya set contains a line in every direction. This is also the work of Zeb de Vere on finite field Kakeya. He used this property, but this property is very hard to use in R3. One reason is that when we have a Kakeya set, if we zoom in, or if we intersect with a large rectangular box, then it no longer has the property that it contains a line segment in every direction. So even though if we don't know the problem, we haven't studied the problem for a while, then we look at this issue, we might think, okay, we should absolutely use the property that a Kakeya set contains a line in every direction. And that's also what people have been trying for many years. But we took a different approach. It turns out that, at least in our approach, this is not the most important part or feature of the Kakeya set. Quite surprisingly, the most important feature is that the Kakeya set lies in R3. So the three-dimensional real space, the space we can touch and feel. But the Heisenberg group lies in C3. So it turns out that the most important property that we need to use is how to distinguish real field and complex field. And there has been a lot of developments in this direction, and it's about that. Let me just digress a little bit and talk about projection theory. So in the past, I would say 5-6 years or so, maybe 8 years, there has been a lot of development in projection theory, and there is this general theme about that we first study a special class of sets called sticky sets, which is sets with similar properties at all scales. For instance, usually a self-similar set is sticky, but the notion of stickiness is more general than that. And these sticky sets usually have some rigid structure. And from those rigid structure, we can usually derive some product of configurations or some, and then this is via the sum product configuration we can distinguish real numbers and complex numbers. I will talk about what sum product means later. And so the general theme in projection theory is first we use Organ's discretized sum product that distinguish real numbers and complex numbers to prove the theorem we want to prove for a special class of sets, that's sticky sets. And then later we use, most of the times we use the theorem for sticky sets as a black box, and then use some induction on scales to prove for general sets. So for today's talk, I'm going to focus on the sticky Kakeya set problem, that is the left-hand side. And for tomorrow, I'm going to show some argument how to use induction on scales to use sticky Kakeya theorem as a black box and to prove the general Kakeya set conjecture in R3. And there are many tools that's been developed in the past 10 years or so. So just to show you that there are other theorems that's proved using this scheme. So first we prove for sticky sets, and then we prove for general sets. So there are something like the Furstenberg set estimate or Furstenberg set conjecture in R2 is also about, it's not just about union of tubes, it's rather about, say on each tube, we only take a few balls, and then we estimate the union of those balls on the tube. So previously, when we talk about union of tube, we take the entire tube. And now what does Furstenberg set estimate says is that, okay, suppose I'm not allowed to take the entire tube. I take only some fractal collection of delta tube balls. And then now I take the union of those red balls. I hope you can see it, and ask how large is the set. And so that is the Furstenberg set conjecture, and this is more general than the Kakeya set conjecture. And so even though the Kakeya set conjecture in R2 was proved like more than 50 years ago, we only managed to prove the Furstenberg set conjecture in R2 2 years ago. So the proof of the Furstenberg set conjecture is first opponent Schmerkin, they proved for the sticky case, and then soon after Kevin Ren and myself, we generalized. We used the sticky case as a black box and proved for the general case. And similarly, as we are going to see today and tomorrow, the Kakeya set conjecture in R3 is also proved using this scheme. While there are still open problems, for example, the Faulkner distance set problem in R2, where the sticky case was solved, but it remains open for the general case. So maybe, are there any questions so far? Okay. Now, for our problem, what does sticky mean? So for different problems, sticky sets might mean different things, because we need to, one challenge is to find the right notion of stickiness for different problems. So for us, the right notion of sticky Kakeya set means that the set of tubes satisfies the Caspar-Wolf axiom at all scales. So let me just show you two pictures. Can you guess which one is? I think I already told you which one is sticky. Okay, so yes, so the left-hand side is not sticky, but the right-hand side is sticky. you can sort of guess from the words, like from the right-hand side, those tubes are like stick together, and so they look sticky. But in terms of somewhat rigorous definition, it means that the white tubes on the left-hand side, if we thicken them to the purple tubes, then we have a lot more purple tubes. So they are not, they do not satisfy the Kastel-Wolff axiom. So remember, the Kastel-Wolff axiom says that there are not too many tubes. And also the tubes cannot be concentrated on in convex sets. The right-hand side, we can see that even though we thicken it to the green tubes, it still satisfies the Kastel-Wolff axiom. So I hope these two pictures tells you like the difference between sticky sets and non-sticky sets. And for tomorrow's talk, we are going to do some induction on scales. And it's important to remember that when we deal with non-sticky sets, this picture tells us that at some scale, if we thicken it, we see a lot of tubes. And we are going to use this property to have some improvement. So here is the rigorous definition. We say that the set of tubes is sticky if it satisfies Kastel-Wolff axiom at all scales. So means that for any row between delta and 1, if we take the set of distinct row tubes covering T, and then T row is satisfies Kastel-Wolff axiom. In other words, for any rectangular box U, the number of row tubes containing U is less than the volume of U divided by the volume of a single row tube. So what does it mean on set of distinct row tubes covering T? So here, as we can see that there are many delta tubes in it. And for each delta tube, we can sort of take a row neighborhood of it. But as we can see that for the delta tubes that are close by, even when we take row neighborhood, they look like almost the same row tube. So for those row tubes, we count only once. So like this one, we count only one green tube. That is what we mean by the set of distinct row tubes. And we can do some pigeonholing such that the number of tubes, delta tubes, is approximately the number of row tubes times the number of delta tubes contained in a row tube, in any row tube in T row. And this can be done by pigeonholing. So that is the key definition of stickiness. So, are there any questions? Yes, yes. Yes, exactly. Yes, yes. That. Yes, yes. Otherwise, this is empty left-hand side, so it holds trivially. Yeah. Are there more questions? Yeah, it's fine to not remember the definition as long as you can remember the pictures. So there are a few remarks to help us digest this definition. First of all, since the row tubes also satisfies the Kastel-Wolff axiom, as we said before, if we take U, the rectangular box, to be the unit box, then this means that the number of T row is less than 1 over the volume of T row, which is row to the -2, up to some constant. So we know that for sticky sets, there are not that many row tubes. And the second remark is that both T row and also the rescaled, the delta tubes in row tube. So what does this rescaled T row mean? It means that, so we have a row tube, and then we take all the delta tubes in it. and then we rescale this row tube to have to radius to do an anisotropic rescaling to have radius 1, and then those delta tube becomes delta over row tubes. So it means that those delta over row tubes satisfies the Kastel-Wolff axiom at all scales. It means that they are sticky. So both T row and both, if we thicken this, so this means thickening. If we thicken our set of tubes, and then this means zoom in. So it means that we take the set of delta tubes in the row tube and then rescale it, means zooming in. So both thickening and zooming in, we still produce those sets of tubes that are sticky, satisfy Kastel at all scales. So this is really important because it's helpful to do induction scales. So when we do induction scales, it's quite nice to have the same property, the sets of the same property whenever we need to deal with some sets. And this B is the key feature of stickiness that we are going to apply, or we are going to study. So this number C is more like the more classical definition of Kakeya set. This C is the notion of sticky Kakeya set in the blog post of Katz and Tao. In the blog post of Tao, that's the argument of Katz-Tao. So this one, the more classical, the old definition of stickiness is a special case of our definition of stickiness. But for the previous definition, it has a meaning that's slightly easier to understand. So for this old definition means that if we have two tubes where their angle is small, where they are like almost parallel, then they have to stick together. So this is sticky. But if two tubes, they are almost parallel and they are far apart, then they are not sticky. So that was the old definition, and this is a special case of our definition of stickiness, means that the set of tubes satisfies the Kastel-Wolff axiom at all scales. So old definition in the Katz. Yes. Yeah, so their definition is more special than our definition. Okay, so the theorem we proved in 2022 says that, so maybe I should just for historical reason, the theorem we've proved for 2022 was for this special notion of stickiness that in their definition, but in our paper a couple of years ago, we realized, maybe even last year, we realized that the same proof holds for a more general notion of stickiness, which is if the set of tubes satisfies the Kastel-Wolff axiom at all scales, then we have the desired estimate. Then the union of tubes has volume approximately. Again, this approximately is up to some delta to the epsilon power. Number of tubes times the volume of a single tube, and the volume of single tube is just delta squared. So that is our theorem, and I would just do a proof sketch ideas, and then we'll talk about some feature of the proof, some components of the proof. So the idea is to study, we are going to do induction scales. So we are going to study the multiplicity. So this mu t, one can visualize as the number of tubes through a typical point. So the formal definition is like the number of tubes times the volume of a tube divided by the volume of their union. So it's just at the typical point how many tubes passing through it. So we are going to let sigma be the smallest number such that the multiplicity is bounded by the number of tubes to sigma for the sticky set of tubes. Right? For all the tubes satisfies the Kastel-Wolff axiom at all scales. So eventually our goal is to show that if we want to show this is true, then we want to show that the multiplicity is approximately 1. So in other words, we want to show that sigma equals to 0. And we are going to do induction on scales in the sense that suppose we know this statement holds for some sigma, and then we want to say that in fact it holds for a smaller sigma. So now here is a very quick question. For what sigma this trivially holds? Yes. So sigma equals to 1, this trivially holds because you can have at most number of tubes, many tubes through a point. With some more work, you can show sigma equals to 1/2, but it doesn't matter. It's okay if we work with sigma equals to 1. Okay. So now let's assume that it holds for some sigma. And the starting point is, suppose we have a worst example. Let T be an extremal example. And to simplify our presentation, we are going to say that, first of all, it has to satisfy the assumption. So T has to be sticky. It satisfies the Kastel-Wolff axiom at all scales. And second, it attains the worst bound. The multiplicity of T is approximately number of T to sigma. And this part is to simplify the presentation. Assume that the number of T is delta to the -2. So this is not true in general, but let's assume this is really the worst case. We have the maximal possible number of tubes. And then because as we said that we can pigeonhole such that the number of delta tubes is approximately the number of row tubes times the number of delta tubes inside one row tube. So also it's by our assumption, we also know that the set of tubes satisfies the Kastel-Wolff axiom at all scales. In particular, this means that T row satisfies the Kastel-Wolff axiom, and also the number of tubes in row satisfies the Kastel-Wolff axiom. So by our definition, the set of tubes satisfies the Kastel-Wolff axiom should have small cardinality. So this means that the number of T row is less or equal than row to the -2, since T row is Kastel. And the number of delta tubes in T row also less or equal than delta over row to the -2, because this is also Kastel. So here is it's simple, but it's we are going to use this argument again. So I'm going to do it very slowly. We know that delta to the -2 is less than row to the -2 times delta over row to the -2. So this together is less than delta to the -2. But we also know that these two numbers are the same. So this is equal. So in particular, it says that both less or equal should be approximately the same. So this means instead of less or equal, they have to be approximately the same. That's a consequence of our assumption that the number of tubes is delta to the -2, and also a consequence of the Kastel-Wolff axioms at all scales. Yeah, this is a baby version of the argument we are going to do later. Are there any questions? Okay, so that's our setup with an extremal example in mind, and we are going to study this extremal example. So because if extremal, then we will see that it should have extremal multiplicities at all scales. And this leads to rigid structure. And this, since it has extremal multiplicity at all scales, we could derive from those rigid structure of some product phenomenon. So the rigid structure will be graininess that we are going to see. And then the graininess and also reduce to some product type problem. And in the end, we are going to use projection theory to study this some product type problem and to derive a contradiction when sigma is positive. So I think for today, maybe I could do one and maybe a little bit of graininess and then projection theory. There are this reduction to some product type problem. The geometry is quite beautiful, but it's also complicated. And also this part is sort of special feature of the Kakeya-type problem. But the other part, like extremal multiplicities at all scales, so this part is pretty general in the sense that when we talk about all other problems that are solved in a similar way, we also have the same extremal multiplicities at all scales and try to use this rigid structure to derive some product type problem. And we also use projection theory to do some contradiction. Are there any questions so far? Okay. So let's talk about multiplicity. We are going to see multiplicity also in the talk tomorrow. So we want to how to say, we'll see basically the same slides tomorrow, but then you will see that when it's sticky and there is something happen, and when it's non-sticky, there is something else happen. So we need to study this picture twice. So first, let's recall that we are at our worst example. So the multiplicity, the number of tubes through a typical point, is approximately the number of tubes to sigma. And we know that the number of tubes is approximately delta to the minus 2. So the multiplicity is approximately delta to the minus 2 sigma. And the goal is to show that the multiplicity should be much less than delta to the minus 2 sigma. And now we have some self-improvement. So here is how we visualize how we decompose the multiplicity. Okay. So maybe let's just do it slowly. If we are interested in this center point, and like the multiplicity is the number of those delta tubes, each delta tube is this yellow tube through this point. So as we can count, the number of the multiplicity here is 6 because we have 1, 2, 3, 1, 2, 3 many tubes passing through it. And we can estimate the multiplicity in 2 ways. So first, we regroup the set of delta tubes in a row tube. So it's like 6 equals to 3 times 2. We have 3 tubes inside this row tube that passing through our point. And this is how we do inductional scales. And then those delta tubes inside row tube, when they intersect the point, since they have very narrow angle, so they stay together for a while. That means that their intersection is, they intersect into a segment rather than a point. So this because they have narrow angle. So they intersect into a segment of length delta over rho. So I think we have seen this segment before. Okay, so they intersected into this segment, and so we decompose the multiplicity into the multiplicity of delta tubes inside row tube, and also the multiplicity of segment, because each segment there is going to be 3 many delta tubes passing through it. So that is the first decomposition, and we call those segments G, that is grains. This curly G means the collection of grains. So the first decomposition means the multiplicity of the tubes is approximately the number of tubes in the row tube passing through a point times the number of grains passing through a typical point. So this is a first decomposition. This holds in general, and this holds after pigeonholing. This is sharp. And there is another estimate that, okay, instead of, this might seem funny because we have this sharp decomposition, but in reality, for many years, people have been, including myself, we have been using the second decomposition. In other words, we, instead of counting how many segments or grains passing through a point, we count how many row tubes passing through a point. So that's the second decomposition. As we can see that in this picture, there are three row tubes passing through this point. So this what does this empty row tube mean? It means that, well, the delta tubes in row tube might not necessarily pass through this middle point. It might be like it's somewhere else. So it does not contribute to the multiplicity. So previously, what people do is say that, okay, the multiplicity is bounded by the number of thin tubes inside row tube and then times the number of row tubes passing through each point. However, this is a key observation in the sticky case. That is that, okay, so since we can apply induction, and we just said that this, after rescaling, is also a sticky set. So this is bounded by the number of tubes to sigma, which is, as we just said, the number of such tubes is delta over rho to the -2. So by induction, since it satisfies the Kessler-Wolf axiom at all scales, by induction, the multiplicity means that the number of thin tubes through this point is bounded by delta over rho to the -2 sigma. This is by induction. Also, because we are in the sticky case, by induction, the multiplicity, the number of fat tubes, row tubes passing through each point, is also less or equal than the number of row tubes to the sigma. And we just calculated or analyzed that the number of row tubes should be rho to the -2. So the multiplicity is less or equal than rho to the -2 sigma. So what do we know? We know that the worst example has multiplicity approximately delta to the -2 sigma. And this is also less or equal than delta to the -2 sigma. So either we have an improvement, or this two inequality has to be equality. So we are doing this trick again. So yes, indeed, they have to be equality. But what does it mean when they become equality? It means that here in this picture, there can possibly have three fat tubes passing through it. It has to, so this cannot possibly exist. So yeah, so as we can see that this is always greater or equal than the fat method multiplicity is always greater or equal than the grain multiplicity, but our calculation for the sticky case by induction shows that the two numbers have to equal. So of course they are not equal. 2 is not equal to 3. So this means that this empty tube shouldn't exist. So that's the very important feature of stickiness, and this key property has been used over and over in other sticky problems. Yes. 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 True. So we know two things. First thing is that this tubes shouldn't exist. The empty tubes shouldn't exist. The second thing is, if we want to improve this bound, it suffices that we improve any of this. So it suffices that if we prove better bound for the number of thin tubes in the row tube passing through each point. So as long as we can improve one of this, we get a global improvement. So that's the two things we learn from stickiness. Let me just, this first thing is quite important, so let me just summarize. So it means that the right picture for extreme or sticky Kakeya set should look like this. There shouldn't be any empty tube. In other words, it means that if a row tube passes through a point in the union of tubes in our Kakeya set, there must exist a delta tube in T row. For example, this row tube passes through this point, so there must exist a delta tube in T row passing through X. In other words, previously there was an empty tube. This should not exist, so there must be a delta tube in this row tube passing through X. So this is X. Yeah. Are there any questions? Yes. Yeah. So the same argument works holds in other sticky problems like even the baby Furstenberg epsilon improvement, and also the sticky Furstenberg. I think there is a chat. Oh, it's okay. Hi, Crystal. Okay. Yeah. So for now, it's a general feature of sticky sets, and from now on I'm going to specialize in the Kakeya set problem. So so here, from now on, it's specialized to Kakeya problem, and we are going to see graininess means that the Kakeya set should be a union of grains using this property, using this property we have in mind. So how do we show the graininess? Since this is so important, I'm going just to copy it. Okay. Okay, so we just said that if T row passes through a point in the union of tubes, then there must be a thin tubes in T row passing through it. Previously, we just analyzed for this X in the middle. But since we know that there are other row delta tubes containing it, so let's say this is X. At the same time, since there are this delta tube passing through X, so we know that this T row, let's say T row, this T row should also contains other points. Let's say this is Y, right, and Z. So first of all, we know that because there exists a thin tube inside T row prime that passing through X, we know the whole segment here. Let me use a different color. We know the whole segment is contained in this in T row in the other one. Yeah, maybe it's easier if I change the color. So if we apply the same argument, so to now, since Y is contained in T row, if we apply the same argument to Y, it means that there must be a thin tube in T row, like a delta tube in T row passing through Y. So in other words, suppose this is Y. We know that there must be some delta tube in T row passing through Y. So this delta tube is here. And similarly, for any other tube in this, for any other delta balls in this segment, we can find other delta tube passing through in direction T row passing through it. This gives the grainy structure because so here this is a segment of size. That's when in the special case when rho is delta to the 1/2. This is a segment of length delta to the 1/2 times delta times delta. So the whole segment in another direction, there are another delta to the 1/2 times delta segments that intersected transversely, and when we put them together, this becomes a slab. That is the grain, a different kind of slab grain. So this becomes altogether. This becomes delta to the 1/2 times delta to the 1/2 times delta grain, slab grain. And this, what we just proved is that any sticky Kakeya set should be a union of those delta to the 1/2 times delta to 1/2 times delta slab grain. So that is the original graininess in the Cas-Tau argument. And are there any questions about this step? And in fact, we know even more than that. So far, we only consider 2 fat tubes through this point. Imagine there is a third fat tube, and we can apply the same argument. And this says that the third fat tube must be coplanar with the 2 fat tubes, because otherwise, we know that in another direction, it also has to be 4, and then we know that locally the Kakeya set is 3 dimensions, and we are done. When we can just apply induction. We can thicken everything and apply induction. So we know that if there is another rho tube passing through it, it has to be coplanar. So now we know that the Kakeya set, the sticky Kakeya set, if we intersect with delta to the 1/2 all, the sticky Kakeya set is in fact a union of those parallel slabs. And the reason why it's parallel is just because if we have a third rho tube passing through it, it has to be coplanar. So this has to be parallel slabs. And this is a lot of structure to play with. And that is the important consequence of the sticky sets. Yeah. Are there any questions? Yes. So here we apply this previous the consequence of the stickiness to the special case when rho equals to delta to the 1/2. The same argument would hold for any rho, let's say smaller than delta to 1/2, but delta to 1/2 is a nice scale to play with because in this case delta over rho equals to rho. Okay. Are there more questions? Okay, so from this structure, and then I'm going to show you very quickly some beautiful pictures, but I won't have time to explain it. And you are welcome to ask me what do they mean. So we know that those red parts are actually how the Kakeya set looks like, and then from those Kakeya sets and those structure, we are going to rescale it, and then try to find more structures using the same argument applied to a rescaled Kakeya set, and so that those structure will eventually lead to some product structure. Yeah, this becomes more and more complicated. It's almost like a video game where you need to navigate on those tubes. So finally, the sum product structure we have is the following. We have a set A in the unit interval, and this set A, whose dimension is the dimension of the Kakeya set minus 2. And then we have 2 sets in the plane F and G. They are one-dimensional sets. And the sum product configuration that we derive from this very complicated picture is that the set A plus F minus G dot product with, F minus F dot product with G is still containing A, where this is the sum product. So here we have minus of two sets of F and F in the plane, and also dot product with G, another set in the plane. So F minus F dot product with G means that we have Z1, Z2, and Y. They are in 0, 1 interval. But when I put a quotation here, it means that they are in a one-dimensional subset of the 0, 1 interval. And then this set is just FZ1 minus FZ2 times Y plus GY times Z1 minus Z2. So I should say that this F just means that it's parameterized by Z. It does not have any regularity. So all we know that this F itself, so this F is not a C1 function. It's not even a necessary very nice Lipschitz function, but it does not have any regularity. So so this capital F is just the one-dimensional set in the plane. And we have this sum product configuration, and we want to draw a contradiction. So this is what we derived from from the graininess structure, and so far it all looks very nice, and we just need to derive a contradiction. However, here is something we need to be very careful, because for now, even at this point, we still haven't distinguished the Heisenberg group, that's our enemy, and the Kakeya set. Because for the Heisenberg group in C3, we can take A equals to R, and F equals to Z bar Z. Z is a complex number, and G equals to Y, comma Y bar. Y is a complex number. So for this one, it still satisfies this sum product configuration, and the dimension of A is like half of the dimension of the complex field. So at this point, we still have not yet distinguished the two sets. And for tomorrow, I'm going to start with how to use projection theory to study this and distinguish the Heisenberg group example and also the Kakeya set in R3. I will stop here. Thank you.
Are there any questions?
They talked a lot about this case, right? And we started with the definition, and then it said, okay, we have this definition for the result of structure, but you don't really understand this because that's very relative, right?
Yeah.
Right? And remember that yesterday you told us that our ultimate goal was we are trying to prove this finitary Kakeya conjecture, which is basically a lower bound of the volume of delta Q. If we prove this bound, then we can bound of output.
Yeah.
So the question is, do we know that there are some, because we have some Kakeya sets, and we are approximating it by this delta Q to delta H.
Yeah.
Right? Do we know that you can set all this approximation?
So I think the Sokovich construction, if you take the limit, yes, then all the approximations.
So do you understand the question very well, or is it an example? You can always kind of interpret it.
So in reality, the sticky theorem we are going to use is also a delta discretized version. So we really need this quantitative version. Means that if it's like sufficiently close to stickiness, then we have some delta to the epsilon bound, and epsilon becomes smaller as we are closer to stickiness. We use this discretized version as an input for our induction, so to go to prove the general case. Does this answer your question? So in the proof, we don't need to like have an actual sticky Kakeya set that goes to the limit. But yes, there exists sticky Kakeya set at all scales. We can just take a like self-similar set in the parameter space, so it should satisfy stickiness. Yeah. Yes. Yes. Which one do you want to see? Yeah, if you want to leave, you're welcome to leave. So here is the picture. So we fixed a row tube, and this row has radius delta to 1/2, and we just said that in each ball it should be a union of those parallel slabs. So this is the picture. And if we rescale this row tube to unit tube, then each of those slabs becomes a horizontal tube, right? And this is, so those horizontal tubes do not belong to the set of tubes that we define the Kakeya set. It just says that the Kakeya set should look like a union of horizontal tubes. So to say that this yellow tube is a tube in the original when we defined the Kakeya set, and this yellow tube is rescaled to another yellow tube, just to say that they are different than the horizontal tube. And also we know that the number of horizontal tubes is on each slice is approximately rho to the -1 plus 2 sigma. This is related to the size assumption we had at the beginning. And so we can parameterize them using this structure that the Kakeya set, rescale Kakeya set is a union of horizontal tubes at each slice. And for different slices, it could have different directions. But in the same slice, they have to be parallel. And we can use the same argument because we know that the union of those rescale tubes is again a sticky Kakeya set. So we can apply the same argument and say that, okay, locally it has to be also a union of those slabs. And so those new slabs we obtain from exactly the same argument should align with the previous rescale slab, which now becomes horizontal tubes. And through this alignment, and then we are going to sort of play some sort of video games in the sense that we need to go from a point on downstairs and go up, and then go through horizontal tubes, and then go downstairs again using the slabs. So those configuration gives us, so as you can see now I'm calculating the coordinates and gives us the sum product configuration. So what this A means, A just means how many slabs are there contained in a ball. So the size of A is really related to the size of the Kakeya set. Yeah, I think I also put this slide online, so if you're interested, you can take a look and see if you agree with me about those coordinates. Thank you.